Okay, so since it doesn't seem like we have too many deep discussion topics, we're going to just do some info updates from various parts all around. And then if this doesn't spark discussion, we'll just break early in that case. So there's a bunch of folks with info updates. I'm just going to go in a random order. Okay, tell us about Pippi moving to PyTorch Core.
Yeah, so Pippi has been around for maybe a year or more. Finally comes to the time like I call it virtualization. Uh, so we are moving into the core as touch.distributed.pipelining as a package. Like we're using the name pipelining as like we are, pipelining your model, right? So we serve two kinds of users. One kind of user have the full model. So what they want is they don't want to rewrite their model into model trunk style. So we'll provide a tool for them to give some annotation, and we do the automatic cutting for them into, submodules or in our terms, pipeline stages. Then there's also another kind of users that will already maybe somehow have the model trunk definition ready. Like then they can connect directly to our manual pipelining UI as well. But both front end will connect to a shared pipeline schedule, like 1F1B, gpipe, interleaved 1F1B, looped BFS, and maybe more coming in the future. And that's our pipeline runtime. So this new pipelining package will consist of this compiling front end as well as the runtime backend. Yeah, that's
Okay,
my update.
any questions? Kai, is there something else you want to add?
No, not much. Thanks.
Okay. All right, moving on. Mark Seraphim, tell us about spirits.
Yeah, so the main big project that like we're hoping to land soon is like a good story for people to like fine tune extremely large like LLMs on like consumer GPUs. So the sort of key pieces of this as a like you can think of it like as an insurance policy is CPU offloading, which is you just dump the optimizer state on CPU and you do your optimizer step there. That ends up being the primary bottleneck for CPU offloading, and that's very heavily mitigated by like a faster fused CPU optimizer. So Jane and I worked on upstreaming something like that in Core. It's there now and just works with FSTP2. The second part of that is that we like, for like a long running pain point in the community has been like the lack of composition between QLoRa and FSTP, mostly because FSTP ignores like integer T types and sort of casts them to float. So like the key pieces of work there were like Driss, who added NF4 support in AO, and Wei, who's now been working on basically making it compose with FSTP by like implementing some ops like torch chunk. So all of this work will be landing soon, and we should basically have some end-to-end numbers to share within like a week or two.
All right, thanks, Mark. Any questions, comments about this? Okay.
Just
Yeah.
just wondering if FSTP2 solved this, integer parameter issue for you or your customer.
Yeah, so like FSDP would solve it with Waze PRs. It's not solved today yet.
I see.
I actually think notably that like it relies on FSTP2 to work as much as I know.
Got it.
All right, thank you. Let's see. Okay, Driss, tell us about flex attention.
Shouldn't have spoken. Yeah, maybe I'll share my quick little doc. Okay, so in a composability meeting a long time ago, Horace and I presented something called score mod. The gist of it is that in the typical scaled out product attention, this is like the very vanilla implementation. there's a lot of flexibility and new work around like what we're calling a score mod, where you take your attention scores and you modify it in some way. Back then we like were looking at the flash attention Triton kernel and just the algorithm, and it turns out it's like easy to inline compute after you've calculated your scores. And this birthed what we called score mod, where essentially like using the Torch compile stack, we are allowing users to pass in somewhat arbitrary functions that will be score modifications and then create a fast flash attention kernel from them. So this is like a little fun prototype example of what someone could do that up. So they call this checkerboard attention. Causal attention is like the preeminent example of this, where actually like I have a code. So let's look at what causal attention is in like terms of score mod. So like this is the score modification for causal attention. If your token index is further along than your key value index, then you just return the score as is. Otherwise, you mask it, and masking is assign the value negative infinity because the softmax will turn this into a 0. Yeah, so this is it. There's a lot of work that we've been doing. There's a fun little project board, I think here with all this stuff. Horace, there's a bunch of fun PRs. Like Horace has a fun PR here, where essentially like makes get item a torch function hook because of scalar indexing causes the item calls to be called. Yeah, that's pretty much it. There's a lot of detail, there's a lot of depth, but
Okay,
this is
I
the
want to ask a
30K foot.
question.
Yeah.
So my question is, what's the general strategy for backwards on these custom attention formulas? Like maybe you haven't figured it all out, but like, what's the general approach going to be?
Yeah, so like this PR is what I've just been working on this week. Essentially we use map is like a good example in the higher ops land. So I'm like using some of the work that Edie's already done here, but we are using AOT Autograd to create the joint graph from the user's score like forward function. And then I wrote up an Autograd function where if you inline the joint graph in the correct location, the backwards formula is right. I don't know if that's enough detail.
So you're going to create a joint graph for the user defined function, and then do you like split it and then like paste them into the
Yeah, that's like exactly it. Yeah.
How do you deal with things that are closed over in the score mod function?
Or no, in this case, we don't split it. We just have like the forward function, and then we have it backwards that is essentially the formula if you just applied activation check 20 on it. So nothing is saved. Does that make sense, Ed?
Yeah, it does make sense. Any other questions from the room?
Does that answer your capture buffers question?
No, actually, the capture buffers question is a different question. I'm also like cheating because Horace told me this was something you were planning to add later.
Yeah, or sorry, capture buffers that
so
require.
So let's say I have a score mod function, and what I want to do is I want to reference some like table that I have hanging out somewhere else. How is that going to work?
So if that table does not require grad, then everything with the existing speculate subgraph infra seems to work. And I think like Horace wrote a really cool like example score mod, which can take any existing score modification and rewrite it to work with NJTs, basically just by doing the correct indexing. And that's like an example of using 2 capture buffers for the offsets and the like sequence lengths. As long as those don't, go for it first.
or like a typical captured buffers actually already work, or they worked until the PR was reverted, I think last night. Yeah, like so like we already support captured buffers and higher order ops. And so then like the way you use a captured buffer in this API is you basically like index into it, and then that indirect indexing just gets turned into a regular load at the kernel level.
Any other
Does that make sense?
questions?
This has interesting ramifications for like the eager implementation though. Meaning like it's not necessarily sound unless you compile with AOT eager. I mean, Horace, correct me if I said that wrong.
I don't know if we have Horace. Horace. Okay, one more question while Horace is fixing his mic. You mentioned NJTs. I didn't know NJTs was related to this. Tell me more.
Well, I think like one of the like preeminent ops for NJTs is SDPA. And Joel can correct me if I'm wrong.
Yeah.
Yeah. And like essentially for attention on NJT, I mean like the nice vanilla case where you have a batch of sequences of different lengths. You can't just do regular attention, and the common way to do that is with like padding and masking. Flash attention has something called the var length API, and this is saying if you provide extra indexing information, you actually don't need to like perform any attention on the extra padded out tokens and mask them out. You can just do it directly on only the do only the compute you need. I think that the score mod that Horace provided today does potentially some extra compute, but it allows you to index correctly. And then in the future, we're hoping to like find a way to support sparsity patterns and not do the extra compute and just get the best of all the worlds.
Okay. Any other questions from the room?
Oh, what do we think about flex attention as a name? Flexible attention.
Seems
And it kind of sounds like Flash.
Name as any.
Okay, cool.
Yeah. Flex and Flash is a little interesting, but that's not that big a deal.
I think we're standing on the shoulders of giants.
You're flexing on Flash.
Cool. Thank you.
Okay. Brian, tell us about some of the stuff that has been banging around.
Sure.
And this can be info sharing because some of the topics I asked people to talk about apparently are resolved, but I think it's helpful like to tell everyone how these things are resolved.
Yeah, sounds good. Let me share my screen real quick. Okay. So I've just been trying to file GitHub issues recently for like outstanding subclass known problems. So here's 3 in the last couple of days. I can quickly go over them. So maybe this one first. So context here is subclasses and export don't really work today. Very concretely, subclasses and export work in very specific contexts. In particular, if you are exporting a model and your model uses subclasses, but the subclasses are just intermediates in the graph and they don't exist at the graph boundaries, then export should work. But if you have any subclasses at the graph boundaries, then you'll get an error today. And in particular, graph boundaries here means if you have any model buffers or weights that are subclasses, or if any of your like forward inputs or forward outputs are subclasses. And 2 use cases have come up recently. One, and people here can correct me if I'm wrong, but one is NJT, where I believe, I'm actually not sure which one it is, if it's like forward inputs or the buffers or parameters will be subclasses. For NJT, I'm guessing it's forward inputs.
Yeah, that's right.
Okay, and then the other one is for some of the AO stuff where Jerry and other people are working on like MX types and like low precision quantization, where you want to have like weights be represented by subclasses that correspond to like a uint4 type or something. Here you'll have weights that are subclasses, and people want to be able to use like AOT inductor. And so they both run into the same problem today. And so for the buffer parameter version of the problem, which in this case is for the like AOTI low D-type precision subclass case, one idea that came up from Ed and Albin in a chat was using parameterizations to solve this problem, where the idea is like, why do we error today? The reason we error today is because if you export a model and your model's buffers or parameters or subclasses, then what you're going to do is export a graph, and you're going to load your state tick at runtime in some like export runtime environment. And the state tick that you load at runtime will have subclasses in it. And that's bad because your subclasses are Python. And so how do parameterizations help with this problem? So parameterizations basically say that the stuff in your state ticks is actually the desugared version of your subclass. And then when you access a parameter in your model, it'll invoke the parameterization. And in this case, the parameterization will construct the subclass and effectively like treat your weight as like the subclass. And then when you export your model, which has this parameterization in it, then the construction of the subclass and then all of the later like compute on that subclass will show up in the trace of the model. And so the subclass construction and all the compute is sort of part of the trace. And that kind of nicely solves the like what to do about state ticks having subclasses in them problem, because now the state that you effectively like removed the subclasses from being at the graph boundaries to forcing them to be inside of the graph because they like show up in construction in the graph. And that sounds pretty nice. And the one caveat is that Dynamo doesn't work well with parameterizations today. And so we'll need to fix that.
Do we know why it doesn't work?
I tested it. I don't know exactly what it's doing wrong, but it does seem like it ends up like running the parameterization eagerly. And by the time we get to AOT Autograd, we end up with like buffers on the graph module that are the actual subclasses. So it seems roughly like instead of Dynamo like inlining the parameterization, it just like runs it. And then that is like what we see in AOT Autograd.
Animesh?
There's a config flag called inline inbuilt NN modules. Can you turn it on and see if it solves the problem?
Yeah, what's it called?
Yeah, inline underscore inbuilt under NN modules. There's NN. Maybe I should do a better name, but yeah.
Sure. Yeah, I can try it afterwards.
Okay.
Okay, if there's no more...
Just.
Yeah.
So like, I feel like I don't. How does this work with no Python? How does this work with no Python? Like, what are you actually building when you run? Yeah, how does? I don't know, I feel like I'm missing something.
Yeah. So you're saying like we have tensor subclasses in Python. Like, how does that work when we're in some C++ environment?
Yeah.
And at least in my head, the answer is that if you write a tensor subclass and you promise that it works with compile, then you're effectively promising that your subclass desugars into non-subclass operations. And so the stuff in your graph will be these like non-subclass operations, and then that's what runs at runtime. And so we're sort of like tracing away the subclass into nothing, and then the graph that we extract and export will be like a subclass-free graph.
So usual only traceable wrapper subclass caveats and all the things.
Yeah. Okay, so that's the parameter buffer case. And then the input forward case for nested tensor probably can't be solved the same way. I guess what I imagine happening is that at runtime, someone is going to be like passing a forward input to their like model in C++. And you're in a C++ environment, so you probably don't have an NJT subclass. So you probably have some C++ representation of your subclass, or you have like the desugared like values offsets tensors, and like that's what you're feeding into your model. And that should work, with the caveat being that like the order of the arguments that you pass into the model, we need to make sure that we get it right, basically, where like in Python, you have your tensor subclass, we call tensor flatten on it, and it gives us back inner tensors in some order. And that basically defines the argument order of the exported model. And so if you pass in some like desugared tensors in C++, then you need to emulate that same order when you're actually calling it. And so there's probably some like bookkeeping we need to do to make sure that people don't get it wrong.
It seems like there's also a pre-processing component to create those desugared values and offsets that somehow has to be injected into there during export. Does that make sense?
Yeah, I can believe that. I guess I don't know enough about how these forward inputs are constructed at runtime in the like C++ inference context. Like if the answer is like we have some notion of like we're constructing values offsets in C++ and passing them in, then I don't know if that happens in a pre-proc step or something else, but.
Yeah, I don't think we've fleshed it out fully yet. I was just thinking that in order to get.
Are you telling us that tensor unflatten on NJT does non-trivial compute?
Say that again, Ed. It was quiet for me.
Sorry, so the question was whether or not there also needed to be some pre-processing when we're turning the desugared inputs into the quote-unquote tensor subclass.
I was thinking like in the exported model, some kind of pre-processing before we like enter into the graph, if the graph takes in the desugared components. Pre-processing on like the inputs that we want to send through to get them in that form.
Oh, okay, I see.
Yeah.
I think I would say there are two things here, and it's mostly a calling convention, but for all the parameters, we are the one that package them and put that into the model. So I think the parameterization here should, naturally handle that. You don't need to add extra logic, because the way we prepare the state dict as being pure tensor only means that this is how it's going to get fed to the network directly. And, the reparameterization that is now built into the network will retranslate that whichever way we want. The only other case is the input to the model that, if the input was supposed to be structured and now you're looking for it in an unstructured way, there is indeed a calling convention that you need to agree on with the surrounding code so that they give you the desugared version. But, this is C++ only, so like they could have the tensors in a subclass already or something. You need some way to interact there.
Right.
Any other questions? Okay, that's subclass plus export. These other two issues are a lot more narrow, so I can cover them faster. But there's a broader issue here, which is that dynamic shapes and subclasses work in some cases and don't work in other cases, and there's sort of a bunch of stuff to disentangle. And here's like one major case that's broken today that has sort of like come up as like not a major blocker, but we should still definitely fix it because it's bad. And the case that's broken today is if you have a tensor subclass and it's a graph output, and you're using dynamic shapes, and your tensor subclass has some non-trivial relationship between the outer sizes of the subclass and the inner sizes of its inner tensors, then we'll just do bad things today. And so like what's going on? So if you're using dynamic shapes with compile and you're returning a graph output that has dynamic shapes, then presumably we needed to do some integer compute in inductor or in the compiled region to compute what the output shapes should be given the input shapes. And today that compute happens in inductor. And when you have tensor subclasses, that compute does not happen in inductor. And that's because the default thing that we do with subclasses is we like desugar the subclass and only put the like inner tensor compute inside the graph for inductor. And right now we kind of like blindly do the wrong thing of we like grab whatever we think the output shapes of the subclasses should be based on what we witnessed at trace time, and we like slam that into the subclass. And that means that today you'll end up with, at runtime, you'll get a subclass that has like Simmons for its sizes, which is very bad. So that is this like specific issue.
Do you have a proposal for how to fix it?
Yeah, so we talked briefly about a proposal. Someone from QuantSite is potentially going to take a look at it. And very roughly, like, there's this size compute that needs to happen at runtime where we have like the concrete sizes of the input subclasses, and we need to get the concrete sizes of the output subclasses. And we do have from trace time like some SymPy expressions that tell us like how to generate those output sizes. And so we need to execute those expressions at runtime. And I think there's some, I think Ed, you added some like interpreter logic for like interpreting SymPy expressions into an FX graph. And so probably we do something like that. And then we just need to decide like what to do with that FX graph. Like, do we send it to inductor somehow, or do we just assume that this is cheap, so we just kind of run it in some sidecar thing?
Do you even have to do this? Like, for example, can you just call dot size on the tensor subclass and then return that as an output for the compiler region? Yeah, what even happens if I call dot size on a tensor subclass? How does that get turned into the desugared code?
That's a good question. It wouldn't show up in the graph today, post AOT Autograd, because you would never see that in the like. Right?
Because if it doesn't show up in the graph, then that suggests that you're also specializing in that case as well.
Yeah, we also do this thing where the Simmons on the outer subclass input will show up as extra graph args from Dynamo. And so I guess I imagine that we use that somehow.
No, but what I mean is, what do you do if I like have a tensor subclass, I do some compute, so I have some intermediate tensor subclasses, and then I call dot size on one of them.
And then you use that size like in some other compute.
Like I multiply a tensor by it or something.
Yeah. We do bad things probably today.
Okay. So I feel like this probably means we should fix that, and then fixing the output case is just a special case of fixing that.
Yeah, I think that's fair. And we probably have to decide what we want to do there. Of like, I don't think we want the like subclass dot size call to literally be in the graph, because in the post subclass graph we don't see that.
Yeah, you're gonna get rid of it when you're done desugaring.
How do you avoid putting that in the graph?
Well, you have to do the same thing Brian was proposing, which is like turn it into a bunch of equivalent FX offs that give you the size using the interpreter thing. So it ends up being the same, but I'm just pointing out that this is like the same problem, even though there's no output involved.
Yeah, that's fair.
Cool. Yeah, the output one like has a weird symptom where the cement leaks out, and then later on, if you try to use it, it gets interpreted as a tensor and it has some weird magic value. But yeah, it is the same problem.
Okay, any questions about this? All right, hit the last one, Brian.
And then okay. Last one. This is also like a known issue that we should really fix, and no one has desperately needed it in the last few months, but it seems like it's becoming more important. So what is the issue? The issue is if you have a wrapper tensor subclass where its inner tensor is not a plain tensor, but instead another wrapper tensor subclass, so they're nested, we don't really do good things today. And one of the main reasons why we even have this bug is just because there's a lot of code throughout compile that calls tensor flatten in a bunch of places and doesn't like generically figure out like what to do if the results of tensor flatten are yet more subclasses that it needs to flatten. So we probably need some recursive thing that just becomes like the util that we kind of use throughout compile. But this breaks today. That is one like known problem. There might be more problems. What are the major use cases? So one is dtensor and float8 are going to do things together that involve nesting in some way. Joel was also telling me about NJT might needing to nest with other subclasses. So we should probably fix this at some point soon.
Yeah, Christian's been talking about re-implementing sparse BSR using NJT, so we would need it for that.
Do we have a basic idea for the strategy on this?
There's an older post that Christian did. I can link it.
Oh, no, I meant for implementing nesting.
I mean, I think the main thing, like in terms of what should happen, it's that AOT Autograd, when it sees nested subclass inputs, it should fully unwrap them into their completely inner components. And then you get a graph of the like leaves of that wrapper nested structure. And the main thing preventing that today is mostly just all the places where we call tensor flatten not doing recursive things properly. And so from first principles, I would say that's the only problem. But there might be more once we fix that and just kind of see what else happens.
Okay, any other questions, comments? All right, thanks, Brian. Alvin, tell us about backends.
Yes. So it's a very quick update, I guess. We have been, I talked about accelerator here before. That was, work towards getting a unified definition around GPU-like devices that run on the side. The C++ code for that has landed, and we're starting using it in a few components. So this is more a FYI. If you see these kind of accelerator things happening, do continue encouraging them. And I think we're making interesting progress there. The second thing is we have a lot of people interested in getting backends. And by backends here, I mean devices working more smoothly with things that are out of core. So I had this interesting diagram that someone wrote. This is not for me, but it's pretty nice to remind people what are all the options on how you implement a device in PyTorch. Things like CUDA that are fully in tree, including the integration, the kernels, and testing. We have some backends that have a key in tree and have the in tree integration code, but the kernels leave out of tree, and a lot of the testing leaves out of tree. Some of them have CI signal that comes back to core, like XLA or XPU. Some of them don't, and they just break, and we don't do much with them. And the third option is this shared key that we have in core called private use one, where we have the basic infrastructure and all the extension points so that people can override it fully from out of tree. And we have a few users for that already, where they have the backend implementation out of tree, the kernels out of tree, the testing out of tree, and everything else out of tree. So that is kind of the current state. One important device in the middle here is MTIA that we are kind of interested in internally. But that's the state of things. I am trying to work, and we are working with a lot of people from the MTIA team, from the NPU team, from the Intel team, from the Apple team, on getting all of these pieces moving forward and making them work better together and more seamlessly. So if you see PRs coming through saying we are reworking the AutoCast API to be device generic, or we are reworking a whole bunch of subsystems to be device generic APIs, this is where all of these efforts are coming from. And so slowly we want to try and remove from our higher level code all the CUDA specific or any device specific code to try and migrate that to more device generic. trying to have this long-term vision where systems like GPT-Fast or GPT, you should be able to change the device as a command line argument, both for backends that are in tree and for backends that are out of tree, would be kind of the North Star here. So there are a lot of moving pieces that we need to get rolling for that, and a lot of partners are working in that direction. And I think that's the main things.
Questions? I have a question. So what's going on with the plugin import thingy?
So the plugin is part of that story of we need to be able for out-of-tree backends to just work without any Python code modification, just by updating the environment. So I think the Intel team is going to go forward and implement the plugin for out-of-tree backends. I think there's some discussion on whether other components in PyTorch might benefit from a similar business. We'll see. But yeah, that's what the current state of the plugin is. It is one of the items in that long laundry list of items of things that we need to fix to basically make these backends as good as CUDA, or as good as ROCm, or like things that are in tree, so that we can actually have our partners build backend out of tree, as a full-fledged feature.
Okay.
Is that satisfying for you?
Yes, thank you. So that is all the topics that I managed to scrounge up. Final call. Sherlock, not to put you on the spot, but anything to tell us about inference and NJTs? No is an okay answer.
Yeah, no update from my part.
Okay. All right, then we will break 15 minutes early. Thanks everyone for coming. See you all next week.